Problem number 43 in blue. 43, blue. Hup. All right, so now, case 1. The rifle is fired straight up with a velocity of 30 meters per second. All right, in case 2, the rifle is fired downward at a velocity of 30 meters per second. All right, so up at 30 meters per second, this was down at 30 meters per second. Now it seems like we don't have enough information because we don't know how far it falls after it goes past this level. All right, so let's just put in this, and this says because they're fired from the same level. Right? So here this one starts at this level. Here this one starts at this level right here. So the idea is we don't know how far below it lands, right? We have no idea where the ground is. So you might say, well, we need more information before we can figure that out. But not so. Here's the deal. We know by symmetry that this thing is going to go up in the air and it's going to come back down. And when it gets back down to the same spot, what do we know about its velocity? It's the same downward as it was fired upward. Okay? And I've said we should take that, I've given that to you as an element of symmetry, but we can demonstrate that that's true by showing for delta y is equal to 0. So I challenge you to do that yourself. Solve for the velocity you would have when delta y is equal to 0. Okay? Delta y is equal to 0 twice, right at the beginning, and then when it passes back through. And I think we actually did this already when we used the timeless equation and we took the positive and negative roots. Okay? So if this is going 30 meters per second at the same height as this, with the same gravitational acceleration, then the amount of time it takes for this one to go, for case 1 to go from here to the ground, and the one it takes case 2 to go from here to the ground, no matter where it is going to be the same. Okay? It's not saying they're fired at the same time. It's saying what's the difference in the amount of time. So since they both start at the same speed, heading downward, and fall the same distance with the same acceleration, they'll both take the same amount of time. We can demonstrate that mathematically if you want, but again, you go back and look at the algebra that shows that that's true. Okay? So now, if this, once it falls past here, is the same as this once it's shot straight down, the only thing we need to solve for in terms of time is the amount of time it takes to go through this part of its trajectory. Okay? So how are we going to figure that out? Let's think about what we know, and we'll figure that. All right, we know that the initial velocity is equal to what?
30 meters.
30 meters per second. We know the final velocity is going to be equal to negative 30 meters per second. We know that the acceleration is equal to g. All right? Do we know the time? I do. It's about 6 seconds. But what else do we know? What do we know for real? This is the implied information. Look at this black line. What do we know? Right here, this tells us what? We're back at our starting position, which is what? Which means that delta y, our displacement, is 0, right? So here we go. Delta y is equal to 0. What do we got? v naught a, delta y. We're trying to solve for something. T. We could throw out any one of those things and still solve, right? Because VOTAT's easy. Yeah. I kind of like throwing out this one right here. Because this one we inferred. It wasn't actually given to us. Okay? So if we throw out that one, and now we got t is equal to we don't know. So we got t, we got delta y, we got acceleration, and we got v naught. And so what equation is that? And that's not timeless, we got time. That's the meat grinder equation. All right, so here's our formula, the meat grinder equation. Delta y is equal to v naught t minus 1/2 gt squared. Okay, in free fall, right? I've already substituted negative g for the acceleration, and we use delta y for our displacement. All right, now we look at that and we go, oh, we got a t, we got a t squared. It seems like, we're gonna have to use a quadratic formula. No, everybody, All right, why don't we have to use the quadratic equation? Okay, because this is 0. 0 is equal to v naught t minus 1/2 gt squared. We can divide through by t, right? We divide through by t, we still get 0 on this side, and we have each on this side and over on this side, each of the terms is reduced by a t. And this, all we're really saying mathematically is that one of the roots of this quadratic equation is 0, right? So now we can just say 0 is equal to v naught t, v naught minus 1/2 gt. And solving for t, we get, anybody?
6.12.
How about 2v naught over g? We're doing algebra still. Okay? And then when we plug everything in, we get t is equal to 2 times v naught, 30 meters per second, divided by g, 9.8 meters per second squared. That's going to give us 1 over seconds. That'll give us seconds, right, dimensionally. So 60 divided by 9.8 is 6 and a little teeny bit. 6 and 0.260ths. What is it?
6.12.
6.12?
Yep.
All right, we call that 6.1, but that's probably too precise. 6.1 seconds is how long it would take to get back to the original position. So that's how much longer the first one would take than the second one, and then the same amount of time thereafter. Okay? So you could ask this question, a different way to ask this question would be, how long after you fired the one up in the air would you fire the one straight down so that they hit at the same time? Okay? You see that? All right. There's our answer for number 43. I'll be able to